All right. Yeah, I totally understand that. Um, so I looked up online to try and prepare for this by getting some practice problems for salt. Oh, I just asked if y'all would like a salt practice problem. So I'm going to go ahead and do one. I looked online to find one, and I couldn't really find any. It's kind of general term, salt practice problem. But I was just going to go over the one she went over at the beginning of class and just change the number so that we can kind of just work through it again. So I'll go ahead and share the screen. There we go. I'll put salt and buffer. We'll go ahead and go over one salt problem. So the way every salt problem is going to be set up is it's going to ask, I'll make this full screen. There we go. Y'all can see that? Yeah. Let me see if I can open up my chat. There we go. All right, so the way every salt problem is going to be set up is going to ask what is the pH of a 0.75, so 0.75 is what she used. We'll use 0.55 just to have a different number in there. Molar solution of KNO2. And we'll use the same salt she used this morning just because it's doesn't change the problem. No matter what salt you have, it just, the numbers would change. So then every problem you're going to be given the Ka. So the Ka for this problem, we're going to go ahead and change. There we go. Ka is equal to, let's say, 3.2 times 10 to the negative fifth. And that is for HNO2. If you remember that, this HNO2 right here comes from the NO2 of this, because if you look at KNO2, that's a salt because you have potassium mixing with a nitrate, or yeah, nitrate, maybe nitrite. Either way, it's mixing with the nitrate, and that's an ionic compound, which is by definition a salt. So any of these problems where you have a potassium or a sodium, as long as it's not an OH following it, that's going to be your salt problem. So I'll go ahead and write that down just so people can see that later. So if you have a salt will be recognizable by any ionic compound being asked in the question. And that KNO2 represents the ionic compound for this specific salt. So then you know it's a salt because you see the KNO2. The HNO2 is coming from the NO2. And then because of that, the strong base, I hate that does that. Strong base, I guess we'll move that down. Right, I'll move this up so we can just work it all together. There we go. There we go. So then your KOH is going to be your strong base. If you remember that list we went over last week on Thursday, if you memorize that, you'll remember that KOH is a strong base. And you know it's KOH because you have the K from here because your NO2 is taken up by the Ka, which is provided. And you see the NO2 in there, so you drop that out, and then you have the K left, and it mixes with OH to make the strong base. So you know that you have a strong base, and because you have a strong base, there will be a weak acid. And by definition, she covered it, I think last Monday, maybe last Wednesday. She said anytime you have a strong base and a weak acid, you're going to be looking for a basic pH, which is greater than 7. So we know that the ending pH needs to be above 7. And once again, I kind of made these numbers up on the fly, so if we get to the end and it doesn't work out, that'll be a little embarrassing. But the math will all be right. It'll just be the numbers that are wrong. So we then have the whole problem set up. We know what we're looking for. We're looking for a pH that's higher than 7. So then we need to set up what we're doing from there. So the NO2 plus the H2O goes back and forth with, or reaches equilibrium with, I guess technical term for that, HNO2 and OH. And that needs to be NO2. There we go. Center that up. All right, so that's the equation we're going to be working with, because you have the NO2, and then this is your water. So you got to remember that this is going to be dropping out of the equation because it's considered the solvent or a pure liquid. So you're not going to be working with that H2O at all whenever you're solving for the pH. So all you're looking at is NO2, HNO2, and OH. So then,
this might be a really stupid question, but how did you get just NO2?
NO2, that is because it's, oh yeah, I forgot. No, that was actually a good point. I needed to make that equation. She started out with the KNO2, which is what you have in the equation. And that's disassociating like that into K plus ions and NO plus NO2 ions. And then you take that NO2 and you bring it down here. And then it reacts with water to create these. And this part, creating these, that's just a part you need to know through knowing the equations. If you have NO2 and it reacts with H2O2, then that'll create the H from here, and then plus an OH, because you'll be left with, if one of these H's and the H2O reacts with the NO2, that makes it HNO2, which goes to that, and then you're left with OH, which goes to here. And that's just something that comes with practice. But good question. So move that down. So then we're going to be starting out with, let me go here, T or T0. So I'll do T is equal to 0. Tab. I think I can get this to look right. NO2 is at 0.75 or 0.55. Yeah, we had it in the beginning. 0.55 molar. Then tab X, or no, tab 0, tab 0, tab 0. Okay, almost got it. Tab. Yeah, there we go. Is that a bit? It's kind of hard to work on a computer like this, but that's not what I wanted. There we go, and there we go. Okay. Yeah, once again, it's a lot easier to do it on paper. I think I figured out a way to do it on paper. I'm sad I couldn't do it today, but for the next in-person lecture, I can do it on paper and it'll look a lot better. Y'all be able to see it and it'll go a lot faster because I won't be doing it on the computer. But yeah, so you start out with the 0.55 molar of NO2, which you get from here. And then everything else is going to be 0 because you're just canceling out this. So you don't need to worry about how much you have of the water because you're not going to be using it. It's not actually 0, but for the purposes of this, it'll be 0. And then since these are your products and this time is equal to 0, you're not going to have any products yet. Then we go to T equals equilibrium, tab. It's going to be 0.55 molar minus X, tab. Water again will cancel out. Then it's going to be X and X. And once again, I'm going to have to find a way to make this look better. Start here, and then I think this will be the way to do it. X. Okay, restart. .55 molar minus X for the NO2. There you go. And then come over here. And this is going to be X and X. There we go. Awesome. So then we know that's how the reaction is going to proceed, right? So then we need to, let me make sure there's no one waiting in the lobby. No, we're good. Okay. I'm always scared that there's going to be someone waiting here for about 10 minutes. So then we start with KB. KB, because we have to solve for KB. KB, and I'm going to go ahead and make this bigger because it's already a little hard to see. KB is equal to the concentration of HNO2 times the concentration of OH, and that's all divided by the concentration of NO2. And that's just products over reactants like we've done for the past acids and base reactions. But the problem is we don't know what KB is. Usually whenever we have these types of problems, this would say Ka, and then we would plug in this value and we would just solve just like that. But the problem is this is KB because it's salt, and just remember that whenever you're solving for a salt, you're going to be solving for the opposite of what they give you. So if they give you Ka, you're going to be solving for Kb, and you got to solve for Kb before you can proceed with the problem. So how do we solve for Kb? We take Kw divided by Ka is equal to Kb. And if you remember Kw, bounce it down a little bit, Kw is equal to Ka times Kb, which means that if you're looking for Ka, you divide the Kb out, and Ka is equal to Kw divided by Kb. If you're looking for Kb, you divide the Ka out, and it's Kw divided by Ka. So we're looking for Kb to find out what this value is going to be. So we know Kb is going to be equal to, and then this is a value you'll need to memorize. Kw is equal to 1.0 times 10 to the negative 14. It's simpler to memorize that than you think. It comes up quite a bit. Anytime you work with salts, you'll use Kw. But yeah, it's very important to remember this is Kw. And then you divide that by the value they gave you for Ka, which is 3.2 times 10 to the negative 5. Bouncing on down. Here we go. And would have been smart for me to grab my calculator. I'll be right back. Okay. So you just plug that into your calculator. 1.0 times 10 to the negative 14 divided by 3.2 times 10 to the negative 5th. And you get 3. Kb is equal to 3.13 times 10 to the negative 10th. All right. And so now you have Kb. Now you can plug in, and it works just the same as we've done for all the other equations. Okay, still good on participants. So now we know I'll just copy paste, that's easier. Control C. There we go. Is equal to, is that subscript? Is equal to HNO2, which is X, OH, which is X, divided by NO2, which is 0.55 minus X. And whenever you're working with a salt, it'll almost always cancel out the X's. you remember whenever we could drop the x because it wasn't going to be important in changing the answer. When you're working with salt, that's almost always going to be the case. Anytime this is a really small number, when this exponent is really large, so -10, that's considered really large. Oh crap, I didn't mean to do that. Or I guess you could consider it really small, but anytime this numerical number, the 10, is really large, you can drop the x. So we'll just go straight into that. It'll be x squared. That's from x times x divided by, what is it? 0.55. All right, cross multiplying. So 3.13 times 10 to the -10th. And then multiply that by 0.55. You get 1.72 times 10 to the -10th. And then that is equal to x squared. So you solve for x. X is equal to square root of the answer. X is equal to 1.31 times 10 to the -5th. And that's your concentration equals the concentration of H. Correct. No. Since you solve for OH, that's the concentration of the hydroxide. Every time you're doing this T0 and T equilibrium, whatever is equal to X right here is what you're solving for. So in this case, it's OH, which means you're going to solve for POH, and then you're going to get pH. So the POH, or POH, is equal to the negative log of this. There. And the negative log of that number. Where's the log button on this guy? Log of the answer. Negative. Awesome. So that is equal to the POH is equal to -4.88. And then we had 2 or 3 sig figs here. So we need to go 3. Oh, that's not negative. We had 3 sig figs, so we need to go 3 decimal places, 4.882. And then we just do 14. The pH is equal to 14 minus that, which is equal to 9.118. And then we check, we got pH is equal to 9.118. We go back to the beginning. pH needs to be higher than 7. That's higher than 7. So we know that this is most likely going to be the correct answer. So that's all the steps you need to take whenever you're solving a salt problem. That's what we worked on last week, and then she gave us one practice problem at the beginning of lecture today. Does that help y'all understand it a little bit better?
Yes.
Awesome.
Yes.
Awesome. So now we will get into buffers. And I think I found one. Screen sharing is paused for a second while I pull up this problem. Let me write it down real quick. Usually I have it written down already, but it's been a bit of a rush today. So the buffer solution we're going to be working with is going to be 1.51. Oh, no, that's not it. Nope. Okay, that didn't. I thought it worked when I first was working on it, but that's not the same problem. So we're going to mix up some numbers and hopefully it works again like it did last time. But either way, the math is going to be the same. So let's bounce this into the middle. Buffer solution. All right, so the main way to tell if the problem you're working on is a buffer, remember if you're on an exam or even a quiz, like you have a quiz on Monday, and it'll be over buffer solution, the best way to tell that it's a buffer solution is it's going to say and. The word and. It'll say you have 0.550 molar of HA and 0.6 molar of this, whatever it is, blah blah blah. But this is the most important part. This is the bold, italicized, underline. This is the part you need to focus on. If it says and in the problem, it is going to be the buffer solution. Every single time. It will never say and this. It'll never say this and this in a acidic, basic, or a salt solution. It'll only be these buffer solutions. So once you got that, you know what problem you're working on, you know exactly what it is, because it can be a little confusing with the other ones. You got to know the difference between these chemicals. But this one, it's just one word. If you find that, then you know what you're working on. So let's say the problem says, what is the pH of a solution of, let's say, 0.20 molar NH3. I'm not going to change the chemicals again just because that's not the important part. It's the numbers. And 0.95 molar NH4 Cl. Yeah, that should work. Yeah. And then it gives us the Kb, which is going to be equal to 2.1 times 10 to the negative, let's say -4th. There we go. And that's for NH3. Oh, 3, there we go. All right, so we have a problem. We see that it says and, so let's go ahead and highlight that, do all of that. Make sure you see that and you're working with a buffer solution because you have a base and a salt. Yeah, it's salt. So then from there, we get into the math, or I guess we get into the equation first. Let's go to the middle. It's NH3 plus H2O, like, oh, that's supposed to be a plus H2O. Like always, it'll be going with H2O. And that goes back and forth with NH4 plus OH. All right. Do you see how we got that equation? Because we have the NH3, bring it down, react it with the water, just like we will every time. One of the hydrogen goes to here, so it makes it NH4, and then you're left with one hydrogen, one oxygen, so that makes an OH. So at T is equal to 0, come over here, and this is the important part where it differs from the very beginning. So we know we have 0.20 molar NH3, 0.20. The water, like always, will cancel out. The NH4, that's when we come over to here, 0.95 molar NH4Cl. Now, obviously, this doesn't say Cl on it, but the important part is this NH4. So you see that, it's 0.95 molar. So you come back here, 0.95 molar. And the OH is at 0. Then at T is equal to equilibrium, you come back over here. And this is, since it's a reactant, it's reacting and it's creating this. it's going to lose percentage, or it's going to lose value from t equals to 0 from t to equilibrium. Because if you start with this much, that's the most you're ever going to have right here. And then you're going to lose some of it so that you can gain more over. Oh, we have 10 minutes. That's fine. We have plenty of time. So you're going to lose x for your reactant. You come over here. This is just ignore that. Then we come over here to the NH4. This is going to be 0.95 molar plus x, because it's a reactant. It starts out just this much, and that is how much you put in there. But this reaction right here is creating more NH4. So you're going to be adding a certain amount, which is the x. And just like that, you're adding x to this, but since it's 0, it's just represented as 1x. You don't have to worry about anything else. So then you come down here and you get to your equation. So you start out, we have Kb right here. And since it's not a salt, you know you're going to be using the Kb. You're not going to be using the Ka. So you have the Kb already, which is equal to 2.1 times 10 to the negative fourth. And that is equal to concentration of NH4 times the concentration of hydroxide.
NH4 or NH3?
NH4, because it's products.
Okay, on that KB, is it supposed to be NH3 then? On that first one right there?
Yes.
Okay.
Yeah, because this is the KB for your KB will be for this part of the equation in a buffer.
Okay, I understand it now. Sorry, I got confused.
You're good. And then on the bottom is the reactant, the NH3, because the water is dropped out. NH3. Boom. All right, and then we know that this is equal, we'll just go back here, equal to, what is it? NH4 is 0.95 molar plus X, right? And then the OH, and that's in parentheses, or brackets, because it's concentration. The X is in parentheses, in brackets, because that's from the OH. And then that's divided by NH3, which is 0.20 minus X. And so the rule when you're working with buffers is that these X's, the minus X and the plus X in the equation, are going to cancel out completely. So right here, that cancels out, and that cancels out, just because they have such little effect on the problem that you don't need to worry about it. So then that transforms this into 0.95, oh, not like that. 0.95x, because you have 0.95 right here, times x, so just 0.95x divided by, I'll go ahead and put that in parentheses so it's easier to see, divided by 0.20. And that's going to be equal to Kb, which is this value right here. We'll go ahead and solve this first. Let's see this up. There we go. And if you do that, 0.95 divided by 0.2 is equal to, oh no, my bad. You do have to bring this down. 2.1 times 10 to the negative fourth. Then you cross multiply and divide. So you multiply this by 0.20 and you get, let's do 2.1 times 10 to the negative fourth times 0.2, which is equal to 4.2 times 10 to the negative fifth equals 0.95x. Then you divided by 0.95, x is equal to 4.42, just be 4.4 times 10 to the negative fifth. And that is equal to your hydroxide concentration, right? So then you take the negative log of this is equal to POH, which is also equal to 4 times 10 to the negative fifth log, second answer, negative 4.35. And we look here, we had two significant figures, so we need two decimal places. So, and it's 4.356, so it'll round up to 4.36. That's your POH. Then your pH is equal to 14 minus 4.36, which is equal to 4.36. It's equal to 9.64. So that's going to be your pH for this problem. And that's your answer. That's how you solve for pH of a buffer solution. It's pretty simple because you get to drop this x out, you get to drop this x out. All you're left with is 0.2, 0.95, and x. Those are the only things you have to work with. And there's no plus or minus signs, so it's all really simple math. Buffer solutions scared me at first whenever I was taking this class for the first time, and then I got to work one. And it was one of the easiest things we did in the class after you really get to know how to do it and get prepared for it. So we have 3 minutes left on the meeting time. And I just wanted to ask if there's any more questions, be it about salts, buffers, or just anything else coming up.
How do you recommend us get better at getting the reaction equations, like the NH3 plus H2O? Yeah,
Sure.
that. Yes.
It's really difficult. I'd say the best way, what I did last year, was Newton, because they offer a lot of different problems. If you look them up online, sometimes it's hard and it's more confusing. If you look up Newton, or if you do all the problems on Newton and then do them again, it'll give you different problems. And then you just kind of understand how they work over time. Just the more you see, the more you understand. It's really a practice makes perfect thing. But
Okay.
you're going to need to know that in this scenario, you're always going to be adding water. And then when you add the water, that makes one of the hydrogens go to your first reactant. And so in this case, it's NH3. So you add a hydrogen to make it NH4. And then you're left with an OH because you have one oxygen, one hydrogen. So it's always going to be your reactant plus a hydrogen and then plus OH.
Okay, cool. Thank you.
Mm-hmm. Any other questions?
I'm good.
Awesome.
I'm
Well,
good too.
I'd say study some Newton before the quiz and let me know how you did on Thursday.
Alrighty, thank you.
Have a good one.
Are SI
You too.
sessions at 5 on Tuesdays or Thursdays as well?
They're 2 to 3.
Okay.
If you
Thanks.
can't make them, I upload the videos to the website. I'm just now starting.
Perfect. Thank you.
All right. Have a good one.
You too.